Okay. Yeah, we set this up on Google Hangouts on air. We've got a YouTube channel. Me and Lonnie Harbor and John McPeak had this little thing going online called JaxVM, where we're trying to promote things in Jacksonville to do with technology. So we've started this JaxVM YouTube channel, and so we've connected remotely through Google Hangouts and YouTube, and we're going to be broadcasting this live on the internet tonight. If you search for JaxVM on YouTube, you should be able to find our channel.
Right now, when you start broadcasting, it will be YouTube, and then you will have it recorded for a later review?
It does it automatically. It's broadcasting live on YouTube right now, and it's recording it. As soon as it's finished, you can go to YouTube, and you'll see it, the recording there. You can look for. I'll tweet it out on Twitter under my Twitter account, Clint Combs, and also under the Twitter account JaxVM, JaxVM.
JaxVM. We stop hearing you. I'm not sure if it's because you're not talking or because something went wrong.
Okay.
But
all right. Can you hear me?
So shall we get started, and you will do the broadcast?
Yep. Go for it.
Okay. So we were starting the round around the room with Mr. Casillas.
So Luis Casillas. We've been doing .NET, Java, and just multi-platform stuff for about 15 years. Been in Jacksonville most of that time, and love technology. And I'm not a fanboy of any specific one. I just love. I love new shiny. But what's nice is getting ahead of it. You wind up, 3-6 years later, when people actually want to do it, you're ready for it. So, and this is one of those technologies I think fall into that category. Get it now, understand it, because it's huge.
I'm Eric Azar. I work here at Availity. I'm a technical architect with APIs. I'm Randy. I work as a contractor at the. Work as a developer and for Veterans Affairs. Working. Technology is a little dated, which is why I like to come here. Keep up with what's going on. We're always 2 to 3 years behind. They've caught up.
Bill Carlson, I work for Health as a Java. Casual trades for all sorts of things. Actually, going to be cheating on JUG next month and giving a talk at the Jacksonville.
Here. I didn't hear who you work for.
Boro Health.
Boro Health.
Barry, I work over at Tech Systems. We thank you guys for all coming, and we'd love to host this. Always interested in picking everyone's brain, so if you'd love to talk technology to someone who the big data stuff right now, we've been seeing a lot of positions out here locally with some of the big data technologies to do. Talk to a few of you so far tonight, just to familiarize myself with some of those. Recruiter, but space.
Sam Starr, principal and developer concept.
I'm Trey Snow. I'm with Tech Systems. I'm Kendra's partner. I'm the Java. I'll learn some more about it.
And let it down. Looking for double.
David Fetch, the project architect for Real. Full stack development.
Oh, which company? I think you.
I'm working as a solution architect. US and other two companies are architect, and mostly I'm working on APIs and mobile technologies. And recently, with HL7 with one contract. I'm working with one of the working integrating your billing APIs.
Hi, I'm Jyoti Chawla. I'm .NET developer. John McPeak. Around the Java developer for Devos.
I also work at FNF, solution architect. Have lots of stuff. And I'm really interested in this just because we started a for search and replacing a Google search appliance, and start to dip our toes into a bit of the big data over there. So,
What's up, Nip?
Fidelity National Financial Title Company. FNF owns Black Knight and FIS.
I'm Eyal. I work at Ability as a Java developer, also interested in big data. Some big data projects here, but it will take a while. I organize those meetings. I'd like to thank Tech Systems again for sponsoring the meetings and the meetup site. I'd like to thank Ability for providing the space. Thank our presenter, Carol.
So we'll go ahead and get started. First, we're going to go over the core components of Kafka or MapR streams. So we'll go over the core components there. Then we're going to go over the patterns, these patterns that are here, and then we're going to go over a couple of real-world examples. So which products are we talking about? Talking about Kafka. I think the title got actually cut off. So we're talking about Kafka, but actually MapR Streams is an implementation of the Kafka API, and that's what my company's product is, MapR Streams. Applicable, the design is the same, the applications are the same as Kafka. Some of the MapR Streams has some added features. So the core components, talking about the core components, basically what's a stream? Kind of like a queue, you have producers are putting events in and consumers are consuming the events. So you've probably seen this before, if you've ever used queues before, but we'll see that there's some differences. And what is streaming data? Here's some examples of streaming data that you now have a lot of types of that are connected to the internet, and you have these events and you want to capture them rapidly and you want to be able to analyze them rapidly. Examples, medical devices. We're going to be talking about healthcare and fraud are the two examples that we're going to look at. So why streams? So a lot of the applications now that you want to have, especially these big data applications, are event oriented. So you have these events like stock prices, data, and you want to be able to react to this with real-time analysis. And so what if you need to analyze the data as it arrives? So typically with big data, what you were doing is because you had a whole lot of data, you were analyzing it in batch with something like Hive or Pig for giving you insights that you couldn't do before because you were able to analyze a lot of data. But it's not very good if you want to analyze something that's happening right now. That's good for analyzing things that happened in the past. Things are good for is analyzing events that are happening right now. So what if you want to organize this data as it arrives? If you're integrating your applications by sharing files or data, this can get very messy. So what you do with streams is you have topics, and that's a logical organization of your events, and that organizes. So for example, here we have topics for pressure, temperature, and warnings. And then the publishers publish to it topic, and the consumers subscribe to the topics that they're interested in. It's a logical arrangement. It processes a high volume of data as it arrives. So for example, something like they're producing a lot of events, and if you don't analyze it as it arrives, you could have a big oil spill. So legacy messaging systems like IBM message queue or something handle those type of events that we just saw, like from an oil rig. So they were typically less than 100,000. And part of this is the design of these typical messaging queue was that you're publishing it, it's written to the database, it's written, you acknowledge it, then the consumer receives it, you acknowledge it and delete it from the database. And this is a lot of reads and writes, and it's not a very fast process. So Kafka and MapR streams have time in order to handle this new internet type of events. So this huge performance hit for non-sequential I/O. Actually, everything about big data, the NoSQL, a lot of it is all about sequential I/O. The disk, well, you want to keep it in memory as much as possible to be fast for reading and writing. But also, if you're writing to disk, you want sequential writes and sequential reads. So that's one of the things that makes it fast. Some other things that make it fast. So this is another thing that makes it fast, is the topics are partitioned. So here we see for each topic, here we have 3 topics. It's partitioned, and these partitions are on different servers, so that these partitions can be in parallel. So the topics, the producers, and they publish round robin, or they can pick the topic that they're publishing to. Those are load balanced, and then also the consumers consume in parallel, and they can be load balanced. So you can have groups, and that can be load balanced. So all that's in order to make it go fast. So you have the combination of the sequential reads and writes to make it a lot faster. This is about Kafka and MapR streams. This is the head of the queue, and this is the tail. And so producers, it's just appending to the end of it, they're consuming from the front of it. Message is appended, it's given an offset ID, and that's the message. So that's what I'm talking about with these sequential writes. It's just appending it, so that makes it a lot faster. And for the consumers, which keeps track of where the consumer is reading. So that's like the pointer for the consumer. And that points to the last message that was read by that consumer.
So we don't delete them.
Jumping ahead of me. So again, like I said, the producers are appending, the consumers are reading. And then the next thing is the events are delivered and that they're received. So it's like a queue. So it's like a queue, but then unlike a queue, the messages are not deleted. Consumers reading these messages, but the messages are still there for other consumers. It has 2 things, you're not deleting it each time, so that's a lot faster, but also it makes these messages are always there for other consumers, and advantages that we're going to go over too.
Are those messages written to disk? Are those messages returned to the disk of the server?
Yes, these are all persisted here. This is persisted. And they're available in memory when they're first written, but they are persisted also. So they can be available in memory for really fast reads and writes, and they're not deleted. Next one is that persisted sequentially as they're written, and they're from disk. And so how fast it can go, you can get up to, with a 5-node cluster, 18 billion events per second, 3.5 gigabits a second, 1.5 trillion events a day. So it's like your typical IBM message queue. And so when are the messages deleted? I think this is one of the differences with Kafka. I don't know all the details about Kafka, but with MapR streams, you can leave them forever. So that makes, we'll talk about the advantages of that also. Delete them. You can set a time to live, and they're automatically deleted after that time to live. But if you set the time to live to 0, they forever. So that makes them available for other consumers. We'll talk about.
Your producer, when the producer's writing to that, is it writing in Kafka or MapR, is then writing to each of those partitions? So it's kind of streaming.
So the producer is producing to a specific partition, and that can be load balanced. So the producer's partitioned to a partition. Does that answer your question?
Yeah. So you had replicas of those on different servers.
Because
okay.
In a minute, yeah. So for parallelism when reading, you can group your consumers so they can read in parallel. And so this is going to be round robin. So here we see that partitions are round robin to this one. So we have partitions, so 2 of these get to 2 partitions. And you have failover. When one of these, then it's redirected to the other consumers. And if a consumer comes back, then it gets its partition. So that's what you can do with consumer groups. Of these consumer groups consuming in parallel, and like I said, not deleting, you can say message to different databases for different purposes. So you can have you can do different things with the same message, basically, which can be used for multiple purposes. About the partition fault tolerance. So what do you do if you need to recover the messages in case the server fails? So the producers are writing to a primary topic. Consumers also consuming from primary. And the primary replicates to the secondary and tertiary. Partition. Here we see that. So here we see, this is, the orange one is the primary partition for each server. Secondary ones. So these are the replicas, and those are just for failover. So the producer is producing to the primary, and the consumer's reading from the primary. One of them goes down. Yeah. So if one of them goes down, this one goes down, for example, then this one will be redirected to that one, producing to that one, and so this one becomes the primary for those 2 basically. So that's what happens for the partition failover.
What about the messages on the that were already written? Do they somehow fail over? Is there some sort of feed between the ones that are still living? Is there some sort of like a RAID drive, right? Like, is there some way that the other ones will recover the lost messages?
Yeah, that's what you're saying.
Well, so this one, it's always, that's the way, actually this is the same way that the HBase and MapRDB work also. It's the same way that, also the file system. It always replicates from the primary to the secondary to the third. Okay. So these are available for failover.
So you write to the one node, to whatever node that it writes to in round robin, but it does synchronize with the other nodes in the cluster.
So the other round, let's say.
Let's see. So this one. So this is the replica for partition 1. Okay. So partition 2. This one goes down. So it's going to go to the replica for partition 2.
Okay. All right.
The server 1 is syncing back to the persistence 2, right? Can you please go back to the previous slide?
So partition 1.
Yeah, partition 1 is syncing back to server 2 and server 3.
Yeah, so they're all going to a different server.
Yeah, so let's say the partition 2 fails, partition 1 is switching back to as primary. And then how can I able to access to server 1 and server 3 because all the previous messages are 1 and 3.
The time you write it to the primary fail, right to the primary.
So
primary fails
is there
before
any master node where it keeps all the partitions and then all the end servers where they are loading, so that when they switch over to a different partition, it automatically switches to the servers where the data is stored?
I'm not sure. So
how the producers will know?
The client library is going to.
Okay, yeah, that is so how they communicate back to the producer to go back to the partition 1. Partition 2 is just a producers. Is there any intermediate layer between?
Are the producers connected to replica set or they are connected to the other partition? Producer should be writing the replica set, right?
So first, that's getting into the architecture of. So that's going to be different for Kafka and for MapRDB. MapR. So for Kafka, it uses Zookeeper, which is, but
so
MapR doesn't use Zookeeper. So
it's connecting back to the HDFS architecture. So where you have the primary node and the secondary nodes will follow back to these partitions.
Right. So then again, MapR has a different architecture than HDFS also. So we HDFS, you have a name node which does keep track of where the replicas are, because then that has a scalability problem. The name node becomes a bottleneck. So MapR does it a different way. So, but there is like a container location thing. So when you're connecting to the cluster, there is a container location database that knows where things are replicated. So that's basically how it works. But with MapR, so it works differently.
Basically, we would like to know more about that.
Yeah. So actually, there's a lot of information about that on our. We have a online training. You can learn about that. So, like I said, it's different than HDFS because there were some problems with the name node in HDFS, and that's a bottleneck. And so, has a better design that is much better for recovery and scalability and things like that. Information about that, like I said, on our on-demand training, on our website and stuff. But yeah, so this one, the client, what in each of these, there's a training actually on MapR Streams that goes into this in much more detail, but for each producer, there's a client library, and it's going to connect automatically. So you supply, we'll look at the code later, you supply just the URL for the cluster. And then automatically the client library is going to then serve in that cluster. That happens under the covers for you. So then for high availability, this is MapR specific. So is actually you can group your topics together in a logical unit, which is called a stream, and then you can manage this, you configure it. configure is replication of the whole stream. So before we talked about replication of the partitions, well, you can replicate this whole topics. So this is like if you want to have multi-data center things. We'll show that. So that's, so for example, if you want to have real-time access to multiple data centers. You have over here in America, you're producing messages and you want to read them over in Europe, for example. You can replicate the whole, this group of topics. Like you can set up this replication and so for example, if one of them goes down, then you can fail over to the other one. That's one use of it. And you can set them up in different ways. So you can have master slave. So this would then provide high availability. The slave can provide backup for the master, for example. You can also have a many-to-one type replication. So for example, if you have your headquarters in Houston and you want to know how well you're doing, you could have all the events many-to-one replicated to the headquarters. And you can also have a multi-master replication. So now we're going into some patterns. And these patterns are from Kafka, really, and also from domain-driven design. Example of the event sourcing pattern. Say that we have, imagine each event is a change to an entry in a database. And so here we have some credit debit events. We have a deposit, some withdrawals. These are going into what we call a change log. The database is just showing the current state. Events have been applied. Will has $80 and Brad has 20. This pattern is we call the event sourcing pattern. The updates, the events are the mutable log for the updates to the database. Does anybody know how replication actually works between databases? Because I didn't know this at first. Actually, how it works is you have a commit log, and the replication is done by the commit log. So this is like, it's a change log, basically. So what happens is sending the change events to the change log. The slave is applying these changes. So that's how database replication works. Really, the idea behind Kafka is it's like an event log. This is what the guy that worked for LinkedIn, I forget, Krebs, he called this the duality of streams and tables. So Kafka was originally developed for LinkedIn. And the database is capturing the data at rest, capturing the data changes. So which one of these could be used to reconstruct the other? Which one makes a better system of record? Create that from this? No, but you can create this from that. You can call this the system of record. System of record. And what you can even do is you can rewind to produce a new view. So for example, a view of the database, but we want to produce a new view. We can reprocess with the consumer. We can start at the oldest message, go to the newest message, and then we have a new view of this stream. For example, to create a cache, an index, whatever your stream has. So this is an example of event sourcing and command query responsibility separation. You have events going into this stream, and then the updates are creating different So the events are the event sourcing. Responsibility separation is is basically whenever you have model is separate from your write model. Write model, which has many different types of views, and it's different from. So the read model is very different from the write model. So the write model is the events, and then you have multiple ways of reading those events. Polyglot persistence. And so what else can you use your stream for? So for example, these events, which you can see how did Brad's balance get so low? You can say who deposited or withdrew from Brad's account. You can trace that back. The log is immutable too. You can see the status of the account /year by rewinding it. We saw you can rewind and replay. Integrity. Can you trust that the data hasn't been changed? Yes, because this event log is immutable. Oh, yeah, I am walking around. Okay, I'll try to stand still.
Oh.
Choosing your mic.
Okay, so then here's an example of fraud detection. Events are, you're at a point of sale device, and the event has the location, the time, and the card ID. And the data center is returning, is it fraud, yes or no? Basically, you want to have a fast response, and you have a lot of events coming in. So this, for this example. So here's a traditional solution. It's the fraud based on card velocity. So card velocity is basically your location and time since your last location. You just bought something in Nashville, and then you just bought something in Spain a couple of minutes later, then it's probably fraud. So that's the idea. Basically what it's going to do is it's going to look up in the database what was the last card used, card velocity, and then it's also going to update the last card views. Also, you can see for this application, if you're doing this and you're sharing this database with a lot of events, reading and writing, then you're going to have a concurrency problem with the doing this is you separate the read from the write. So what we've done is last card used from the database, read, and then the last card used into the event queue. Queue will then write the last card use, update the last card use in the database. So here we've separated the reads from the writes. So that's another example of the command query separation. So we're separating the read model from the write model. Another thing we can do is we can have multiple views. So we can have, besides just updating the last card use, we could do analysis of this card location history. We could have some other numbers of this data. And then we can also have multiple fraud detectors to have better performance, better scalability. So basically what we're doing is we're propagating the events, not the table updates. So this is from Klepman, who also worked at LinkedIn. Interesting. He was comparing domain-driven design to what he had done. He was working at LinkedIn, like I said. Okay, so enterprise software to internet companies, which would be like the banking and healthcare. That's the hard part. The business rules is a hard part. For internet companies like LinkedIn, the scalability, that you have the number of events, the amount of events was the enterprise software was the compliance, the security. Then these two different ideas came. The event sourcing comes from domain-driven design. Processing comes from the internet companies like LinkedIn. Interesting. So now going into a real world solution for fraud detection. So what you do for credit card fraud detection is a little bit more complicated than the velocity that we talked about. Was what you do is you have this historical data, track the features from that data. So the features, but some of the features are card velocity, but you'd also use some other features, profile, things like that. And you're going to then build a learning model, machine learning model, and use that to predict. And the way that you do this is that you transactions, and then you use this training set to build this model, test that to test that. Then when you've built this model that can predict if it's fraud or not, then you can use this model in real time on streaming data to see if it's a fraud or not.
Is it like a 20%?
The test set?
The training set.
Training set, typically you divide this 80 to 20, 70 to 30. Data scientists at MapR have done this with real banks, and there's also real customers that are doing this, MapR customers. So what happens is you have then these events are coming in, the credit card events. They're coming into the raw queue. That's just the raw events. And they're going to be processed. It's going to first look up some profile information about the person from the database, like information about that, like the age or things like that, features that you're going to use in the model. So one of the features would be the last location, for example, looking at the last location. Then put this in the model to predict if it's fraud or not. Then this process is going to publish this it's going to publish the enriched events, publish any frauds that occur as alerts. Then these queues are also going to be, so all the raw events can be stored on the file system for analysis and building the model again. And then alerts can be stored in the database. This might be also stored in the database. So here's another real world solution. This is Liaison, which is a healthcare exchange provider. So it provides services for healthcare. It also provides other services. So it has this Alloy platform, and they were doing B2B for, I think, over 10 years. What they were doing was they were ingesting data, transforming it, and then sending it to whoever was consuming it. They started getting asked to do more services, to store the data, master management of the data, which is deduplication. So they were asked to provide more services to the consumers of this data, to the producers and consumers of this data. So that's what they have now. They have this Alloy platform. So they're providing this as a service for consumers of data. And we're going to look at a couple of use cases that they have for healthcare. They have some other use cases for a healthcare exchange, and they have records coming in. Challenges are that you have very many different data models for the data, security and privacy issues, and HIPAA compliance. So this is one of their products. This is the Georgia. And what it is it's providers are publishing data, so clinical data, financial data from doctors' offices. There's also, this is also connected to the state health exchange. Data viewer and analysis of this data to answer queries like, what are the outcomes in the entire state on diabetes, for example? Or are there doctors who are doing this better than others? So in order to answer these type of questions, you need all the events. So basically, they're storing all the events for the state of Georgia. Another application that they have is they have for labs, they have something called EMR Link. Lab data coming in, and so the lab orders are coming in, they're going to the radiology.
Shutting down.
Just my NetBeans quit. Okay. Okay, so you have these orders going into the labs, and then you have the results coming back. And basically what they do is they match up, they're going and coming at different times. So they're and also the order is composed of multiple things. So they're matching up requests and providing that for. And they're also doing this with compliance. So they have to meet the HIPAA compliance, things like that. This is an example of just in 2015. So that's just to show that the compliance is really important. Example, Target for 2014, quarter 4 had negative 440 million for that quarter because of their breach, and Anthem, their breach. So that's just to show how important security is. Another thing is this is showing the importance of having different views of the data. So one thing that they do is they do linkage or deduplication. So if you have the same person and you want to find out if it's the same person, for example. You can do this with a graph database. You can find relationships between entities. Do this with a graph database than it is with SQL. Do, for example, is here, for example, you have a patient. This prescription by this provider to this doctor.
It looks like when this happened, Clint lost the view of the slides.
Oh,
I don't know.
Okay. I don't see how to do that, though.
Maybe you should.
I think it's in the upper left corner of Hangouts.
Okay,
You can
okay.
click the green arrow.
Okay. No.
What's up?
This example. So this patient went to this provider and got this prescription, and then another patient went to the same provider and got the same prescription. Name is similar. So with a graph database, you could find this relationships much easier than with SQL, because between the different and a graph database. So this is just to show that with different views of the same data, you can view that's most useful for whatever you want to do. So the graph databases can be very useful. So we saw that LinkedIn developed Kafka and Hadoop was developed by Yahoo. Is that they developed these products for their purposes, but they didn't have to worry about things like compliance for healthcare and things like that. Kafka worked really well for LinkedIn, but it might not work for application. So that needs to have all this compliance. This is their architecture, and I'm going to go over it in the next slide. So what happens is the raw data is coming in to a preprocessor, which is doing things like removing the ID, the important ID identification.
Yeah,
masking, right? That's it. Yeah, so it's doing things like that. It's putting it into the stream, which is the mutable log. And then those are putting this into different views. Applications. So in the microservices are providing services for these different applications. So it has different views. It has a key value, a search engine, a graph, database, a time series database, and also just a log on the file system. And then if it wants to provide another view, it can. We talked about before, since the messages aren't deleted and you can have multiple consumers, you can have multiple views, each view providing a different purpose.
That right there, the immutable log, you're doing something different. That would better than.
Oh, no. Well, no. It provides an immutable log. It just immutable log also. The things that AppArt provides is like integrated security, some of those features that Kafka doesn't have. That's the main design. So it definitely. So so the smiley faces are for the data lineage, audit logging, encryption, replication for disaster.
So it looks like we lost Carol there. We'll keep the stream going just in case they rejoin, but if not, I'll be shutting it down shortly. Anyway, we'll wait a little bit. Okay, so I think we'll shut this down. Doesn't look like Carol's going to be reconnecting. Anyway, check us out. Search for JaxVM or Jax_VM on Twitter. You can also look for JaxVM on Facebook. Anyway, reach out, connect, tell us what's going on.